Okay, welcome back. We're going to continue along the lines with Chapter 2, Position, Velocity, and Acceleration. Okay, so we have here a graph of position versus time, x versus t. X is in meters and the time is in seconds. And we would like to use this graph for position versus time to plot a graph for the velocity versus time. And we know, so how are we going to plot it? Well, we will use the definition of velocity or average velocity. Remember, the average velocity is the displacement, which is the change in position over the change in time. So clearly here, the position here is changing at a constant rate because the slope is the same. The same thing here, the position here is not changing at all. And the position here is increasing steadily at some constant rate. So we will divide this into three parts for the time between 0 and 2 seconds, the time between 2 seconds and 4 seconds, and the time between 4 seconds and 6 seconds, and we will calculate the velocity in each of those time intervals. So on the time interval between time t and 4 seconds, and between 0 and 2 seconds, that's this portion here, we will get the velocity or the average velocity. In this case, because it's linear, the velocity will actually be the instantaneous because the rate of change here is constant because the slope is constant. So at any rate, so it will be the position at 2 seconds minus the position at 0 seconds divided by the change in time, which is the time at 2 seconds minus the time at 0 seconds. Okay. The position at 2 seconds is 0. I'm sorry, the position at 2 seconds is -4, and the position at 0 seconds is 0. So it will be, at 2 seconds it's -4, at 0 seconds it's 0, divided by the time, which is 2 minus 0, that's 2. And so this is -2. So the velocity, or the average velocity, is just -2, if you like, meters per second. So during this time interval between 0 and 2, the velocity is simply, I will draw it in red, is simply -2. Just -2 all the way through, all the way here, -2. Okay? Then what? Well then, in fact, I shouldn't say inclusive here because at the end points, it's there is an abrupt rate of change here, which is, you will see it because the velocity will be the derivative of position, and you cannot take the derivative here if it's a sharp edge like this. It's not a smooth function. And so let's look at the velocity during this interval between 2 and 4, between 2 seconds time and 4 seconds. The velocity, the average velocity, will be x at 4 minus x at 2 divided by 4 minus 2. Okay. What's the position at 4 seconds? At 4 seconds it's -4, and at 2 seconds it's also -4, so it didn't change. So I always like to put parentheses like this so you don't confuse the minus signs. So it'll be -4 minus -4. Well, number minus itself will be 0. So the velocity here is actually 0. And here, which is 0, which makes sense. The object hasn't changed its position. It just went to x equal to -4 and just stopped there. It's not moving. Now it will change its position. And look at the slope is positive. Here the slope is negative. Slope here is positive, so the velocity will be positive. And so it will be, now on this interval between 4 and 6 seconds, that the velocity will be x at 6 minus x at 4 divided by 6 minus 4. Clearly 6 minus 4 is 2. The position at 6 seconds is 6 minus the position at 4 seconds, it's -4. -4. And 6 minus -4 is 6 plus 4, which is 10. And 10 over 2 is 5. meters per second. So the velocity here would be 5. 5 would be somewhere here. So on this interval would be 5 meters per second. That's it. Right? So now, what is the definition? This is the average velocity. How about the instantaneous velocity? Well, let's look at it. So here we get a piece of chalk. We will define the instantaneous velocity. Instead of averaging over larger periods of time, remember we said the velocity, the average velocity was the change in position over the change in time. The change in time, you could wait for an hour. You could measure the position now and the position an hour later. That gives you the average velocity over an hour. But if you want to know the velocity really close to right now, maybe you should average over a minute. Or maybe you should average over a second. Or maybe a millisecond. So the closer the measurements you do in time, the closer they are to each other in time, the closer you are to the instantaneous velocity. So if we take the limit as delta t goes to 0, then we have the instantaneous velocity. Graphically speaking, here's how it looks like. Here's time, here is x, and let's say the position looks something like this. If I want the instantaneous velocity here, what do I do? Well, I will look at the average velocity. I will say, this is the time here, t, time t. I will measure the position here. This is x at time t. And then I will wait a little bit later for an amount delta t, meaning t plus delta t. So the change in time is the final time minus the initial time. T plus delta t minus t, that's a delta t. And then I will measure what the position is at that time. That's the position at t plus delta t. And I say, what's the average velocity? Well, the average velocity is the change in position. The position went from this to this. So it changed by this much. That's the change in position, delta x. And this is the change in time, delta t. And the average velocity will be delta x over delta t. So that's the rise over the run. So it's the slope of the line or the line secant connecting these 2 points. If we shrink, if we let delta t get closer and closer to 0, then we get the slope of the line that's tangent, not secant, the line that's tangent to this function, position function at time t. And that's what we call the derivative, dx t. Okay? So the velocity is the time derivative of position, and just to look ahead, the time derivative of velocity will be called the acceleration. And that will be our focus. We will focus on motion at constant acceleration. But equipped with calculus, we can handle any motion as long as we know its function explicitly. So, for instance, let's say I give you a position function. Here is time, here is x as a function of time, and x maybe looks something like this. Maybe it looks something like this, and then it just flattens like that. And I say, what is the velocity as a function of time? Let me call this point here A, and this point here B, and this point here C. The velocity is the derivative. So, or the slope of the line tangent. The slope of the line tangent on this interval here, from here to here, it's negative, and then it becomes 0, and then it becomes positive. So it starts being negative, and then becomes 0 at A. Let's say it's linear, maybe. It will increase, steadily until it becomes 0. And then it becomes positive, and then it is still positive but decreasing, so it becomes positive until this point here, point B. It is positive. But then here, it's still positive, but it decreases. It's decreasing until point C. And at point C, what happens? It's horizontal, it's flat, meaning the slope there, the slope of the line tangent to a horizontal, is 0. So then it becomes simply 0. That's v of t, velocity, as a function of time, just qualitatively speaking. By the way, this point here where the derivative changes, when it changes from an increasing derivative to or an increasing slope to a decreasing slope, is called the point of inflection. That's where the second derivative will be 0 at that point of inflection. Okay, so that's that. Let's look at so this is the velocity versus time, the instantaneous velocity. Let's take an example here. Let's say I give you example. I give you the position versus time. So x is a function of time. This is not x times time. This is position as a function of time. It's just like how you write in calculus f of x, a function of x. This is position is a function of time. Is equal to minus t cubed plus 3t. And of course, x is in meters. Position is measured in meters. And t is in seconds. Alright, seconds. So for question A, I'd like you to find x. Find x when t is equal to 2 seconds. B, I would like us to draw a graph of x and a graph of v. Sketch a graph. So graph x of t and v of t on the interval, for the interval t between 3 and minus 3. So minus 3 and 3. Okay. And that's it. So first, a point that's often overlooked. You might think, how is the position in meters when the time is in seconds? Because, I mean, if I plug in seconds here, 3 times seconds, that's 3 seconds, would be seconds. So how is the position in meters? The reason for that is because this number here, 3, will have units such that when you multiply those units by time, it will be meters. So the 3 here really has units of meters per second, so that when you multiply it by the units of time, which are seconds, you get meters per second times second. They cancel and you get meters. And the same thing here, there is negative, but there is like a 1 here, like 1 times t cubed, we just call it t cubed. So there is a 1 here, but that 1 has units. And it has units of meters per second to the 3rd power, per second cubed. So that when you multiply it by t cubed, which is seconds cubed, they cancel. So you get meters. So that's how this is usually understood, that whatever those constants in front of the t or t cubed or the t to whatever power, they are such that, so that x, when you multiply everything, you get x in meters, and t is in seconds. Okay. In math, usually you work in non-dimensional. You don't worry about dimensions at all. You can non-dimensionalize this. Okay. So let's not worry about that at the moment. Anyways, so you get this. It's a nice, smooth function. So for part A, let's do the solution. For part A, what's the position at time t equal to 2 seconds. So the position at 2 seconds will be, well, you just plug in 2 seconds here, so you get minus 2q plus 3 times 2. And what do we get? You get minus 8 plus 6, that's minus 2. So minus 2. So the position at 2 seconds is at minus 2 meters. For part B, they ask us to graph v and x of t, but to graph the velocity, you have to find the velocity. We know that the velocity is dx dt, is the derivative, dx dt. And derivative of a sum is the sum of the derivatives, so we take the derivative of the first. Remember, when you take the derivative, the 3 comes down and you subtract 3 from the power, so you get minus 3, t to what power? Well, you subtract 1 from there, so you get 2. If you have trouble with derivatives, or if you forget, you have to review that as soon as possible, because this course, while we do use calculus and we try to review it, it's not a course on calculus. Notice, I never mentioned even the precise definition of the derivative or of the limits, or I never mentioned, I'm not going to mention the mean value theorem or the intermediate value theorem, or even the fundamental theorem of calculus. It's hopefully, I hope that you do remember those, or at least have a practical understanding of them. So anyways, so when you take the derivative of minus t cubed, it becomes minus 3t squared, plus the derivative of 3t, derivative of t is just 1, so you just get the 3. So plus 3, that's the velocity as a function of time. Okay, sounds good. Now how do you graph this? The book says just, again, in calculus you can use the curve sketching by using derivatives and second derivatives to find the concavity, whether it's up or down, the points of inflection, the maximum, the minimum, and so on. But it's a physics class, so the book says, hey, go ahead and use your calculator to sketch it, or whatever. So I'm going to just sketch it using the calculator. So they ask us to sketch between 3 equal to, this is x, this is t, between t equal to minus 3 to 3. Minus 3, minus 2, minus 1, 1, 2, 3. And how does it look like? It will look something like this. It has a maximum and a minimum here at minus 1 and 1, and then it will decrease like that. Actually, it should be like right before 2. I think it's like 1.7 something. Anyways, you can sketch this. A good program, if you're online, you can go to Wolfram Alpha. Wolfram Alpha. You can just Google that. And then it has a really nice curve sketching. I might do a video on how to use it. Okay. And then the velocity is a function of time. I know at the minimum here, the velocity would be 0, and at the maximum, the velocity would be 0, because the velocity is the derivative. The derivative gives you a function for the line tangent, and the line tangent here is 0, has a slope 0. The velocity starts being negative, and then it becomes 0. So it starts being negative, and then it becomes 0 here. And then it becomes positive, and more positive, and then it becomes still positive, but then it starts to slow down, and then becomes 0. So at some point here, it reaches the maximum, and then it's still positive, but then it goes back to 0 here, and then it starts to decrease. So it's a concave down parabola, which makes sense. This is a parabola. The graph of the velocity is a parabola. All right? So that's that. Looks good. Now, a question becomes, if you have the position, you can find the velocity easily, take the derivative. How about if you're given the velocity and asked to find the position? Well, if you go forward by a derivative, if you go backward by an antiderivative or an integral, definite or indefinite integral. And that's what we're going to talk about. So I'll talk about that in the next clip, about the going from velocity to position using antiderivatives.